Hello all, welcome back to another video. In this video, I'll be explaining how to design a sequential detector using Mealy model. I have published a few videos on the course of logic design and the solutions of the university questions of logic design. I have given the link of all these videos in the description box. In this video, I'll be explaining about the sequential detector. So let us move on to the video. A sequence detector is a sequential machine which produces an output 1 when the desired sequence is detected. It produces an output 0 at all the other times. It finds the desired pattern from the bit stream. Bit stream means a combination of zeros and ones. For example, it can be of 8 bits, 0, 1, 1, 1, etc. like that, of 8 bits. And your sequence detector is going to detect a particular desired pattern from this bit stream. That desired pattern can be, for example, 0, 1, 0 or 1, 0, 1, 0, etc. A sequence detector will detect this desired pattern and it will give a 1 as output. And it produces the output as 0 at all the other times. Let us design a sequence detector to detect the sequence 1010 if the input sequence is 011011010. Suppose we want to design a sequence detector to detect the sequence 1010 and say that overlapping is permitted here. Now you will be wondering what is overlapping, without overlapping and with overlapping. So here they have given a condition that is overlapping is permitted. This will be explained with this example. For example, if the input sequence is 01101010, that is, this is the bit stream given to the sequence detector. This is the bit stream given to the sequence detector. From this bit stream, the sequence detector has to detect this sequence. So this is the desired sequence. You have to keep this in your memory. This is the desired sequence or pattern. So your sequence detector has to detect this pattern from this bit stream. So this bit stream consists of 8 inputs, 1, 2, 3, 4, 5, 6, 7, 8 inputs are there. These inputs should be given to your sequence detector one by one. Suppose this is your sequence detector. This input has to be given to the sequence detector one by one and you have to get the output from this. So this is your input. Let that be x of t. X of t. So first time x of t equal to 0. This is the first case. 0 will be given to the sequence detector. It will give you some output. Next 1 will be given as the input to the sequence detector. It will give you an output like that. So let us see what is the output for this sequence. Output for this bit stream. So this is the bit stream. Suppose input 0 has been given to the sequence detector. What is the output here? Output is 0 because the sequence that you have to detect here is 1010. This is the desired sequence that you have to detect. So what is the first bit in the desired sequence? It is 1. What about this bit? This is 0. So this first bit doesn't match with your present input. Therefore, the output is 0 because that is not the desired sequence that we need. Now it will take the sequence detector will take the next input. Next input is 1. But there is a possibility that this is the start of your desired sequence. 1 0 1 0, thinking that your sequence detector will give an output 0, though the first bit of your desired sequence is 1, because the sequence is not complete. For a complete sequence, you have to get 1 0 1 0. Therefore, here the output is shown as 0. Now, next input is 1. 1 1 doesn't make the pattern that you need here. The desired sequence is different. Therefore, the output is 0. Again, the next pattern is 0. So, the sequence detector thinks that maybe this is the starting of the desired sequence, but still the output is 0 because it is an incomplete sequence. Now, it will take the next bit, the next input will be given to the sequence detector. Again, it will have a hope that maybe if it gets one more bit like 0, it will complete one sequence, but still here the output is 0 because the sequence here is incomplete. It has got an incomplete sequence. It is only 1 0 1. The complete sequence is 1 0 1 0. Now, in the next input, that is 0, when it gives 0 as the input to the sequence detector, it will detect the desired sequence 1 0 1 0 and it will give an output 1. So, here the sequence is completed. Now, I will talk about this overlapping and without overlapping. First, I will talk about without overlapping. Now, you assume that suppose 2 more bits are here like 1 0 1 0, then your sequence detector, once it has detected the sequence here, it will go to the next bit and it will check whether it can form the desired sequence from this bit, but still the output is 0 since the sequence is incomplete. It will take the next bit. Since the sequence is incomplete, it will give the output as 0. Here also it is incomplete. When it comes to this point, it will get another sequence. This is the second sequence and it will give the output as 1. This is just an assumption I have told you in order to make you understand what is without overlapping. So, this is without overlapping. Now, let us come to the concept with overlapping. Let me erase this off. Now, let me explain you what is with overlapping. With overlapping means, so this was your bit stream 1 0 1 0, one more 1 0 is here. Okay. So, for overlapping, what it does is it will take the last 2 bits of this sequence. This is already the first sequence. This is the first sequence with the white one. This is the first sequence 1 0 1 0. Now, I have drawn this flower bracket for this yellow color flower bracket. This forms another sequence 1 0 1 0. So, you can notice that this 1 0 is used for the first sequence as well as the second sequence. I will complete the second sequence output. Output of the second sequence here, it is 0. When it reaches this 0, it will complete the second sequence, that is 1 0 1 0 1 0 1 0. Therefore, the output is 1. So, this is overlapping. In overlapping, the same bits can be taken as the starting point of the next sequence. Now, we have to draw the state diagram. At time t1, the machine is assumed to be in the initial state A. While in this state, the machine can receive the first bit input either a 0 or 1. In any states, the machine can receive the input as 0 or 1. That is, there are only two possibilities. That is, 0 or 1 can be given as the input to the sequence detector. So, in the first case, that is in state A, if the input bit is a 0, that is, the machine receives a input 0, the machine does not start the detection process. Why? Because the first bit in the desired sequence is what? It is 1. The first bit in the desired sequence is 1. So, it remains in the same state and it will output a 0. Therefore, we have to draw an arc starting from A and terminating at A and label this as what is the input given? 0, and what is the output received? 0. Why the output is 0? Because the sequence has not been detected. Now, if the input bit is a 1, I told you there are only two possibilities for the input. It is 0 and 1. The first case 0, it is over. Now, if we are giving the input to the sequence detector as 1, the detection process starts. So, the machine goes to next state, that is state B, and it will output as 0. It will go to next state, that is state B, and it will output 0. The input given is 1, the output is 0. Why the output is 0? Because the sequence has not been detected yet. But why the machine has gone to the next state? Because the machine thinks that the input 1 is the first bit of the desired sequence and it is going to complete the sequence, and therefore it has considered this bit 1 as the starting of the desired sequence. Therefore, it has moved to the next state. But it has given the output as 0 because it is an incomplete sequence. Now, while in state B, now the machine is in state B, the machine may receive a 0 or a 1 bit. Again, the conditions are this: either it can receive a 0 or it can receive a 1 as the input. So, this is the condition. Now, the machine may receive a 0 or a 1. If the bit is a 0, the machine goes to next state. If the bit is a 0, machine goes to next state. Why 1, 0? Because the next bit in the desired sequence is 0. The machine thinks that it is going to complete the sequence. Maybe 1, 0 is the first part of this desired sequence and it goes to the next state, but the output that it gives is 0 because it is an incomplete sequence. Now, the previous two bits are 1, 0 as I told, and it might lead to a valid sequence. Thinking that in mind, it goes to next state C. If bit is a 1, if in this B state, the machine has received a bit 1, then two bits become 1, 1. This 1 as well as one more 1. It is not 1, 0, it is showing 1, 1. 1, 1 is not the part of the valid sequence. Valid sequence is 1, 0, 1, 0. So, 1, 1 is not a part of the valid sequence. Since overlapping is permitted, this second one may be used to start the sequence. So, the machine remains in the state B itself, that is here itself, in state B itself, and it will give an output 0 because the sequence is not detected. Now in state C, while in state C, the machine may receive a 0 or a 1 bit again. These are the two possibilities, either 0 or 1. So in state C also, the machine is going to receive either a 0 or a 1 bit. If it receives a 0, the last 3 bits received will be 100. See, when the machine reached B, it had 1 bit here. When it reached C, it had 2 bits, that is 10. Now when it moves to, now when it receives a 0 or a 1, when it receives a 1, it will move to the next state. Next state is D. The machine moves to the next state when it receives a 1, so that this state will become 101. Machine moves to the next state in order to make the first 3 bits of the sequence, but the output is 0 since the sequence is incomplete. But when the C state receives a 0 instead of 1, if it receives a 0, what will happen? The sequence that we get here is 100, which doesn't match with our required sequence. The required sequence is 1010, but this 100 doesn't match with the required sequence. Therefore, it has to reset so that it will go back to the beginning state itself, that is to A state itself. When you give a 0, the output is again 0 because the sequence is not detected. Now in state D, the machine may receive a 0 or a 1. If it receives a 0, the last 4 bits become 1010. If it receives a 0, because already this 101 has been completed till D state, if it receives one more 0, the whole sequence is completed here. Okay, so in this D state, the machine may receive a 0 or a 1. If it receives a 0, the last 4 bits becomes 1010, which is a valid sequence, and the machine outputs a 1. Here the important point that you have to remember is, since overlapping is permitted, the machine can utilize the last 2 bits 10. You have to remember this concept what I have told. This is the last 2 bits of the first sequence. Last 2 bits of the first sequence. This is the first sequence, this is the second sequence. So it can use the last 2 bits 10 of the first sequence to get another 1010 sequence, that is the second sequence. So the machine goes back to the state C. The machine goes back to the state C, giving an output 1 because your sequence is detected here. In the other case, which is the other case, when the state is when this D state receives a 1, it will go back to B state because this 1 can be considered as the first bit of the next state, but the output is 0 because here the sequence has not been detected. When the sequence is detected, the output is given as 1. Here already in D state, when we have given a 0, the required sequence has already been detected here, that is 1010 has been detected in this D state. Now we have to draw the state table. We have to draw this table from the state diagram. You have already drawn the state diagram. By seeing the state diagram, you have to write the state table. So which are the states that we have used here? A, B, C, D. A, B, C, D are the 4 states of the sequence detector. When the sequence detector was in state A, it had received 2 inputs, that is x equal to 0, x equal to 1. These are the 2 inputs. So when the state A, when the sequence detector was in state A, when it received input 0, it was in which state? It was in state A itself. That you have to write here. A, it was in state A itself. And what was the output here? The output was 0. The output was 0. Now under this x equal to 1, you have to check at state A, when this state received the input 1, what was the output? 0 was the output, and the machine had moved to state B. Therefore, you have to write that here, state B with the output 0. Similarly, in B state, when you have given a 0, it has moved to which state? C state. So that you have to write here C comma 0. 0 was the output, and when you have given 1 as the input here in B state, 1 as the input, it was in which state? B state itself. And what is the output here? The output is 0. Write that here. Similarly, you have to write for the remaining one also. Remaining states C and D. For D, C1, B0. Now the next step is, that is step 4, reduce standard form state table. Here you don't have any redundant terms, so no need to do anything. You can move on to the next step. Next step is state assignment and transition and output table. So you have to write the transition and output table from this state table. Here what we are going to do is, we are assigning the values for the states A, B, C, D. You are assigning the states. The state assignment is done here. For A, I'll assign the value 0, 0. For B, 0, 1. For C, 1, 0. And for D, 1, 1. Similarly, you have to replace the values of this state A, B, C, D in all the other places as well. So under x equal to 0, you have A comma 0, where 0 is what? 0 is the output. This 0 is the output that you have to write here. And what about this A? Instead of A, you have to write 0, 0. Under x is equal to 1, for B, you have to write 0, 1. And what is the output here? The output is 0. Similarly, in the next state, in the next row, C. Instead of C, you will write 1, 0, because you have assigned C as 1, 0. So write 1, 0 here, and 0, this is the output. This output should be written here. Here B means 0, 1. You have assigned this as 0, 1. And the output here is again 0. Similarly, you can write the remaining. Here you will get 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0. Wherever the sequence is detected, there you will write a 1. The remaining will be 0. So this is your transition and output table. The next step is to write the excitation table. In order to write the excitation table, we have to choose which flip-flop we are going to use here. Here I have chosen D flip-flop, and in the excitation table we have to write the present state, input, next state, excitation inputs. We have to find the excitation inputs and the output. So the present state is represented with small letter q1, q2. input with a X and the next state with capital letter Q1, Q2, and the excitation inputs as D1, D2, and then the output. So here I have used 2 D flip-flops because there are only 4 states, 0, 0, 0, 1, 1, 0, 1, 1. Now from this transition table, we are going to write the excitation table. So the first state for A equal to 0, 0, that means Q1, Q2, that is present. If the present state is 0, 0, the input given is 0, the output or the next state is 0, 0. Output or the next state is 0, 0. And what is the last? The output y is equal to 0. That you have to write from here. Y is equal to 0. Similarly, you have to write for the next state when 0, 0, when x is equal to 1, for 1, when the input is given as 1. When you give the input as 0, the next state is 0, 0. When you give the input as 1 for the first state, that is state A, when you give the input as 1, what is the output or the next state? Sorry, not the output. What is the next state here? It is 0, 1. And what about the output? The output is 0. Similarly, in the next state is 0, 1. The B state or the next state is 0, 1. When you give 0 as the input, what is the output that you will get? Not output, I always say output, it is next state. What is the next state that you will get here? It is 1, 0. And what about the output? The output is 0. Again 0, 1, that is the next same state. Same state when you give the input as 1. Once you will write 0, then you will write 1. That is first you will give the input as 0 to the sequential detector, sequence detector, then you will give a 1. Similarly, for the next state, you will give a 0 and a 1. At that time, what is the next state? Next state is 0, 1. The next state is 0, 1. And what is the output? The output is 0. Similarly, you have to write for all the stages. All the states you have to write. This is 1, 0. When it is 1, 0, it is 0, 0, 0, and output is 0. Again 1, 0 when the input is 1. What will be the next state? Next state is 1, 1, and the output is 0. Again when the next state 1, 1, when the input is 0, you will get 1, 0, and here the sequence is detected, therefore the output is 1. Again in the last case 1, 1, you give the input as 1, the next state is 0, 1, the output is 0. Now the advantage of choosing D flip-flop is whatever is your next state, you just copy down that here in the excitation inputs. This is the excitation input. Just copy down this here 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1. So this is your excitation table. Now the next step is find the expression for the output, that is y, and also for D1, D2. D1, D2 separately, and also for the expression for y. First we will write the expression for y. We know that the in Mealy model the output is the combination of the present state and the input. So this is your present state and this is the input. So, where you get the output as 1, we have to form the corresponding expression from here, from Q1 Q2 x. So, you will get Q1 Q2 a complement of x, that is x bar. This is your y, or the output. Y is equal to Q1 Q2 x bar. Now, you have to find the reduced expression for D1 and D2 separately. For that, we have to draw a K-map. K-map for D1 and D2 separately. So, let us draw a K-map for D1, which consists of 8 cells, Q1, Q2, Q2x, Q1, Q2x, which is 0, 0, 0, 1, 1, 0, 1, 1, 0, 1. Now, you have to place the ones here in the corresponding cells. See here and place the ones, that is 1, 1, 1. Now, group this. You will get the expression as D1 is equal to Q2 x bar plus Q1 Q2 bar x. Similarly, you have to draw a K-map for D2. Plot the K-map for D2. This also consists of 8 cells, Q1 Q2x, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1. Place the ones here. 4 ones are there. 1, 2, 3, 4. Place those ones here and then group this so that you will get D2 is equal to x. Now, the last step is the implementation. That is, you have to draw the logic diagram of the sequence detector, 1, 0, 1, 0, using D flip-flops. So, here I have already drawn the D flip-flops. D1, the input is given as D1 and the output is Q1 bar, and the second flip-flop is D2 with output Q2 bar, and clock have been given to both the flip-flops, and one extra NOT gate have been written here. We give X as the input to that NOT gate in order to get X bar as the output. First of all, let us implement this. D2 is equal to X. Let us implement D2 is equal to X. So, what you have to do is just connect this X with the input of the second flip-flop, that is D2. That is over. Now, you have to see the next equation, that is D1 is equal to Q2 x bar plus Q1 Q2 bar x. We have to implement this one. So, first of all, we will draw this Q2 and this x bar should be given as an input to a AND gate in order to get what? Q2 x bar. And the next term is Q1 Q2 bar x. Q1 Q2 bar x. For that, connect this Q1 to another AND gate which has how many inputs? 3 inputs, Q1 Q2 bar x. So, you have connected Q1. Now, you have to connect Q2 bar. This is Q2 bar. Q2 bar, this can be given as the input, the next input to this AND gate, and we have one more input here. Which one is that? X, that you can take from here, this X. X is given as the input to this AND gate, and now you have to use another OR gate here in order to complete this expression, that is Q2 X bar plus Q1 Q2 bar X. We will connect a OR gate here, and the output can be given to this D1. So this is over. D1 is equal to Q2 X bar plus Q1 Q2 bar X. We have one more expression, that is Y is equal to Q1 Q2 X bar. Y is equal to Q1 Q2 X bar. So where is Q1? We can extend this. This is Q1. You can draw a AND gate here, which is the next expression, next term, Q2. Q2, you have to extend Q2 from this. This is your Q2. So we can extend from this Q2, and which is the third input? Third input is X bar. You can take X bar from here. This is the X bar input. Give that to the AND gate, so that you will get Y is equal to Q1 Q2 X bar. Y is equal to Q1 Q2 X bar. So this is the design of your sequence detector 1010 using D flip-flops.